In this question, we're told that a fluid, and we're given its fluid properties, is forced through a circular tube with the dimensions that are shown. So you can see it's a 4mm diameter pipe, and we're also told that a differential manometer measures the pressure drop across 2 meter length. You can see it's just broken here, and we're asked that when to find the velocity in the tube when the differential reading is 9mm, and we're also told the density of the manometer fluid. So again, this is a pressure loss problem. So start off with Bernoulli's again. Okay, so we write it out and include the pressure loss term on the right hand side. So we can immediately make some simplifications to Bernoulli's equation. Because it's a horizontal pipe, we know that Z1 is equal to Z2, and therefore these two terms will cancel. And also, because it's a constant diameter pipe, we know from continuity what goes in must come out. We know that the velocity at 1 and 2 will also be the same, and therefore these two terms will cancel. Therefore, this Bernoulli simplifies down to that the static pressure on point 1 is equal to static pressure at point 2 plus the pressure losses. Now we can find the differential pressure between 1 and 2 from the general manometer formula. So you'll probably, if you're not sure where this came from, go back and look at the lecture on fluid flow rate measurement, where I derive where this has come from. But basically, for a horizontal pipe, you can show that the change in pressure between the 2 points is equal to the density of the manometer fluid minus the density of the fluid in the pipe times by gravity times by the difference between the fluid heights. Now we also know that the pressure loss in this pipe, assuming that it's laminar, and that's the assumption we're making here, is given by this relationship. So therefore we can equate the two. We can equate the pressure drop is equal to the pressure losses. So if we substitute these two formulas down here, then we end up with this relationship. Now we're trying to find the velocity in the pipe, so we can substitute in the volumetric flow rate here for the area times the velocity, as we've done in the last equation. So now we've got all the information. We've now got a formula where we know everything. We know the two densities, we know the height between the two liquids, we know the viscosity of the liquid, the length of the pipe. Well, we don't know the length of the pipe, but we know the distance we're going between, and the radius of the pipe and the area. So we can rearrange this to work out the velocity. So if we rearrange that as we've done here, and then substitute in all the values that we've got from the question, then if you go through and put it all into your calculator, you should find that the velocity is 11 times 10 to the minus 3 meters per second. And again, although we've got this final answer, that isn't the end of the question. During this analysis, we made assumption that the flow is laminar. That allowed us to use that pressure loss formula for laminar flow. So we need to check that assumption is correct, because if it's not, then this isn't the right answer. So with the velocity that we've got, we work out the Reynolds number for the fluid flow in the pipe. So we've put in the density and the viscosity and so on. We find that indeed we have a Reynolds number of 22, which is much less than 2000, and therefore the flow is laminar, and all the calculations that we've made are valid.